Uh, Today we have with us Dr. Purab Shah. He is a senior lecturer in the Design Engineering and Mathematics Department at Middlesex University, London. He received his PhD in Electronics Engineering and Communications from the University of Plymouth, United Kingdom in 2008. His research interests broadly are in performance and system modeling of Internet of Things, digital twins modeling, autonomous networks, and AI-inspired smart systems with collaboration across Turkey, Italy, Switzerland, Kenya, India, and Pakistan. He has published 80 plus research paper and has served as a reviewer and technical program committee member for many international IEEE conferences. He has received funding from UKRI, British Council, and EPSRC, and serves as the PRC member for the UKRI. He has served as an academic advisor to several startups in the UK and has been an invited guest speaker for over 10 workshop conferences, online and face to face, since 2022. So, welcome to session, Purab sir, and you can start now.
Thank you. Just starting the presentation, so just give me a second. Right, can you all see my screen?
Yes, we can see your screen.
Okay, so good afternoon, everyone.
Can you
thank you for
pardon
inviting
for a
me.
minute? Can you put in full screen mode?
It is full screen, yeah. Is it not?
No.
Should be now. 1 second. Let me do this. Share screen again. Entire screen. And then we should be okay. Now is it okay?
Yeah, fine. Yes, please
Yeah.
go ahead. Yeah, please go ahead.
Okay, so good afternoon, everyone. I'm Purab Shah, as introduced earlier. So I work at Middlesex University in London, and I have quite a few, ties with Indian institutions, especially IIIT Hyderabad, IIIT Sri City, IIT Delhi. So those are the three institutes where my key collaborators are, and I collaborate quite often with them on projects, on papers, and other things. Today's talk is about digital twins, and just to give you a brief introduction to digital twins and use cases for critical infrastructure safety. So the critical infrastructure safety is a area which is not very well defined. What do we define by critical infrastructure safety? Is something that is an open question. But from governmental point of view, it is different. From technology point of view, it is different. From user perspective, it is quite different. So we will go into it as we go along in this discussion. So my agenda for today. Uh, I'd like to give you a brief overview on what our perspective of digital twins is, the life cycle and the architecture, multiple use cases within specific industries. So automotive sector, for example, manufacturing sector, and other critical infrastructure use cases as well. When we talk about digital twins, what is the modeling? What is the architecture? What is the technology stack per se? I'd like to discuss that as well. Some threats alongside with it, where the safety aspect comes in. How safe can we keep our data? Which I'd like to briefly go through that as well, and then go through some challenges and trends and case studies, and with some question and answers if time permits. So we'll go through that. So starting off with digital twins, how do we define a digital twin? To give you a very simple example, IoT, so Internet of Things, we have devices which are, for instance, how to say, which we use sorry, 1 second. So Internet of Things. So we devices which we use in our day-to-day lives. So nowadays we have EV charging, so electric cars and EV charging. EV charging, they talk to a particular cloud network. They provide you access, they build you, and all those aspects. The underlying technology for that is, of course, wireless communication or wired communication. In general, communication networks. Um, they send information, so monitoring information, payment, and other information that is sent across, that we define to be is somewhere which is you know either a digital model or a digital shadow. Okay, we can mimic for monitoring, for predictive monitoring, maintenance purposes. But unfortunately, the only thing that the owner of the EV charger is going to be able to do is to restart the device. Is they are not going to be able to do anything further than that in terms of functionality. If I want to add any further functionality where I am able to control that particular EV charger based upon the car, based upon the type of the car, based upon what amps does it require, what current it requires to charge, what is the battery capacity, and all that monitoring that happens. And based on that, a decision is made in the cloud and then pushed to the physical object, which is the EV charger in this case, for actuating the amount of current to go through. That we define as a digital twin, because we can physically observe what is the behavior of that EV charger, but in a virtual world. So, as an example, thermal aspects for a EV charger are very critical. You do not want the EV charger to heat up to an extent where it's going to burn out and cause catastrophic failure. So that is one of the aspects where the thermal monitoring based upon the temperature that where the car is charging, and the temperature probe is going to give that information to the virtual world. The virtual world, which means your digital twin, is going to determine that how much capacity and what is the cutoff, how much temperature variation is there. Based on that, the current needs to be drawn by the car for charging. So that is where we define a complete digital twin. So it is bi-directional communication and actuation happening between the digital world and the physical object. Okay, so that is where we define this, the digital twin as a representation of, as a high fidelity digital mirror of the physical object, where the digital twin evolves synchronously with the physical entity throughout the entire life cycle. So, as an example, as the EV charger slows down, as it ages, as the components become older, there are some sort of predictive maintenance and monitoring aspects that need to be done, that also will be encompassed within the digital twin of that particular physical object, in this case the EV charger. So um, it's a virtual representation of real world entities, and it is used for number of aspects. People want to run simulation to see what would be the state of the physical object in the next 10 years, next 5 years, for monitoring purposes. So I gave you some examples, and optimization, another example of temperature monitoring, that you don't want the EV charger to be heating up quite significantly, because that can cause issues. So you are optimizing it by making sure that the current that is drawn by the car is at a stable level, and you increase the lifespan of that particular EV charger. Uh, Moving on, just to give you a brief history of digital twins. It was an original idea coined by Michael Greaves in 2002, so almost 23 years ago, as a conceptual idea for product lifecycle management. This was more towards manufacturing, devices and manufacturing units, from which this idea has come up. That how can you provide predictive maintenance, monitoring, and control, remote control of manufacturing units. Going back to the reality of it, so if the Apollo 13 space mission, which failed, if it had a true digital twin, would it be possible that those oxygen tanks that exploded and caused catastrophic failure, where the entire crew had to come back instead of landing on the moon, then that landing on the moon would have been possible, because from Earth, from the digital twin itself, and from the edge device which is embedded within the spacecraft, things could have been monitored, things could have been controlled, and they could have been somehow managed for that explosion not to take place. Um, from history to where we are now, we are actually going from a single digital twin. So simplest example of that, electric vehicle charger, EV charger. From electric vehicle charger, if I have one charger and a digital twin of that, but I have 10 of them in a row, then I could have digital twins, a network of digital twins. And if I have, let's say I'm the owner of the charging network, and I have one in Karnataka, 10 20 in Karnataka, 30 50 charger units in Kerala, and across the entire region. How do I control it? How do I monitor it? So then comes the feature which we define as the federated network of digital twins and twin of a twin. So I have smaller units which I can replicate them as virtual replicas, and those are my digital twins. But then I have a top at the upper layer, where I say, how do those federated digital twins and network digital twins work? So I need to orchestrate at that point the federation of multiple digital twins, and I need to have the software control for that as well. So moving on, our version of definition for a digital twin: it's a self-adapting, self-regulating, self-monitoring, and self-diagnosing system of systems. So it is not just one unit, but a system of multiple systems. As an example, again, manufacturing units would have multiple systems which are separate. So if you have a car manufacturing unit, you have the engine, somebody manages it, maybe a robotic control system is managing the engine part of it, the doors part of it, the body, the chassis, the wheels, the motors, etc. All of it, they are separate units. But if I can have the virtual replica of that as a system of systems, and with the following properties, which is the adaptation, regulation, monitoring, and diagnosis, then I can define it to be a true digital twin. Okay, so characterized by a symbiotic relationship between the physical and the digital or virtual representation. Um, Choice of enabling technologies. If I were to pick one technology, it would be Internet of Things. Anything that is connected via internet or via a network, whether it is a local network or whether it is a internet network, as long as a device is connected and it is able to produce some sort of data, then that is my key enabler for technology, for digital twins. Okay. Supporting services. So why do I need digital twins? We have some sort of monitoring purposes, we have some maintenance and other things that we need to do in systems or in manufacturing units, which is more than enough. I can monitor, I can have a nice visual dashboard, but then I need to call somebody and say, hey, go quickly run to this place, there is a problem on the manufacturing floor. We don't want to do that, but instead we want an automated system, which is where the operational efficiency comes in. Hence the supporting of services which add operational efficiency as well as business value to the physical entity. Um, Going back to that aspect of enabling technology. So if I look at the tree here, okay, on the right hand side, the tree basically is telling me that My key enabling technologies, which is artificial intelligence and machine learning, distributed computing, Internet of Things, industrial Internet of Things, and cyber physical systems. They are the key enabling technologies, VR, AR as well, so virtual reality, augmented reality, etc., to give me multiple use cases of those digital twins. So you have logistics, you have smart cities, you have automotives, manufacturing, wireless communication, so your 5G, 6G networks, Open RAN, etc. Even healthcare. So healthcare digital twins, a key, very important area. Can I call it to be critical infrastructure? Pretty much yes. At that point, robotics. Where do we use robotics? We use robotics in not just in industries, in a closed environment, but we now bring robots out in the world to fix potholes, to make roads, to construct things, to help deliver food, etc., to people. So there are multiple use cases there, and the aspect of digital twinning for each of those is quite novel. Why do we need the replica in the virtual world? Why would I need something for automotive sector? So autonomous cars, very popular in the current day and age. From electric cars, we are now shifting towards autonomous cars, so another shift in the automotive sector. And where we see that driverless cars, driverless taxis are going to be the future. Even drone based taxis, so flying taxis, they are going to be the future. We do not want to be in a situation where safety is forgotten, but it is embedded within. And the only way you can do that is if you have a virtual replica of it and you have full control of that physical system in a virtual world. Okay, so that is where these use cases belong, and enabling technologies are. So what is the purpose? Bringing in intelligence to provide seamless monitoring, analysis, evaluation, and prediction of complex systems. I can run within my digital twin a scenario, and I can say, okay, I'm traveling from A to B today. We already have Google Maps and other APIs telling us that between 10 and 12 there is a lot of traffic, there is this, there is that, etc. But they do not update on real time, but near real time. So they are updating information in near real time, that there is an accident, avoid this particular road, etc. By the time, personally speaking, when I drive car here in the UK, if I have not turned my navigation on and I've reached to a point where I'm stuck in traffic, Google Maps may have already said, but unfortunately, Google Maps tells me the information once I'm stuck in the traffic, not prior hand, so not a priori. The idea here is to have that simulation and complex capability within the digital twin with historical data, with current information coming in to simulate and provide information to the user for near real time execution. So, hence, the idea is that yes, there is potential for the digital twins, but where and how? Do we want to have digital twins for pretty much everything? No. There is, of course, the cost and implementation trade-off that exists. So we need to be looking into that as well. And the idea is that a digital twin should last the whole life cycle of a physical system. So as the physical system evolves, if I add a new sensor in, I should be able to add a new sensor and update my digital twin accordingly. So it needs to be like a modular block based approach. So what is the digital twin ecosystem? As you can see here, you have a user, which is the supervisor. So that human in the loop is always going to be there. It is not basically completely automated process, but near automated process. Okay, we will still require that user to be part of within the loop of the digital twin ecosystem. I have a real world system here. I am using multiple sensors. So as a smart city, I will have sensors deployed across the city for pollution monitoring, traffic monitoring, crowd congestion, etc. And I'm sensing that information and I'm sending it to the twin. The twin, using different types of analytics and AI based approaches, is going to then actuate and give information back to this real world system to say what you want to do is based upon your service based requirements, you need to be performing a particular task. So that is where the actuation comes in. So live dashboards, live information is what the analytics and the AI is going to be providing based upon what sensing it performs and what models we have for our digital twin. So thinking about that and key enablers. So what sort of services can we offer in this scenario? We have simulation. We can also run what if scenarios. We can perform optimization. We can use AI and machine learning. So those are my different services and enablers. And on the left hand side, I have a real time monitoring. So I have a digital dashboard, and I have via IoT, so via my key enabling technology, which is connectivity, I can connect to a number of devices. So I can connect the house, the car, the units inside the house, units within the, your surveillance systems, uh, your construction sites, your manufacturing units, and so on. Why and where is the trend going? So if you look at this trend here from 2024, and by type of the digital twin, we are looking at system twin, right? The system of systems. If you look by 2035, we can see a substantial growth over here. Parts twin is equally significant, but it matures by the time you reach to 2030, roughly. Then 2030 to 2035 is not maturing quite at a high rate. But if you look at the system twins, there is significant, increase over there between 2030 to 2035. So the idea is that we want to go towards the route where we are able to mimic those systems to precision level of the processes of the product itself and the parts. What are the parts made up of? If there is a conveyor belt, I need to know as a owner of the company, for example, to say when I need to change that conveyor belt without having problems in the unit and without the unit breaking down. Rather than calling out a maintenance engineer on an emergency, I can the system will generate a routine inspection for the maintenance engineer to come in and replace the conveyor belt. So that is where that direction is, and that is where the market trend is in terms of, you can see the size. So current market size is roughly around 12.8 billion. But look at that, where it is going up to 2035, from 12.8 billion to 240 billion. Critical infrastructure. When we call critical infrastructure, my road network, bridges, my connectivity to from people driving cars going to one place to another, that is critical infrastructure. Airports, another critical infrastructure aspect. Nuclear power station, coal-fired power stations, any hydro, geothermal power stations that I have, they are all part of the national critical infrastructure. For the UK, one of the critical infrastructure is logistics. Uh, as an example, UK imports a lot of food products. UK does not have the capability to generate the food for the population, all the food. Hence, they import from all across the world. If that logistics network, which is maritime transport, all the food and other supplies coming via the ship, are somehow having a problem, or if there is a crash in the system, or if the system is hacked, then that's the end of, you know, uh, uh, day-to-day living for people in the UK. So the government has, pushed quite a lot on critical infrastructure resilience. Uh, Again, nuclear power stations. So nuclear power stations have a lot of, gain, but at the same time they are a security risk as well. So we are looking at safety, we are looking at security, and all those aspects within why digital twins are so important. So benefits, I've already discussed this quite in depth. Reduce the cycle time, boost productivity, diagnosis, so predictive maintenance and monitoring, operational cost reduction. Yes, for sure. If you do not have any breakdowns in your system and you can predict maintenance, routine maintenance calls, then that operational cost is going to be reduced significantly. Just to give you an example, most cars have a timing belt. Okay, that timing belt, normally they say, okay, after 8 years you should change it and replace it. A very big cost. You need to lift the engine up, you need to go to the timing belt, you need to replace the timing belt. But while you're replacing that, you have multiple rotors as well which you need to change, and gaskets that you need to change. If that was based on a predictive basis, because the quality, yes, the quality is very well controlled for the timing belt, but still some cars have wear and tear more often, some cars have less. So if there was that predictive model that existed, then you are going to reduce that cost drastically. Okay. Efficiency of engineers, the engineers, half of the work is done because of predictive maintenance and monitoring. They already know where exactly the problem is, and they are only coming in to fix that particular point. So there is no requirement to go through the entire process of fault finding. Instead, you are going straight to that point and looking and changing the part, and job done. So quite a few benefits over there in terms of, the technology for digital twins. I'll give you a perspective here what exactly happens, in terms of the life cycle of the digital twin and what tools are required. So if I go start from here, that I create a reference model, okay, for which is the software version for the digital twin. I can have 3D models, simulation, emulation, use of big data analytics at that point, and then I'm going down to visualization. For visualization, I need, of course, analysis of the data that I have collected from my sensors and other aspects. Then I go deploy those using artificial intelligence tools. So cognitive services, artificial intelligence based services, human machine interaction, which then feed into optimization and decision making of multiple machines. So I have collaborative machines that belong here. And then from there, I also have who are my enablers to do all these parts. The key enablers are here, the communication technologies and the interaction taking place between the digital world and the physical world, which is enabled via cloud platforms, cloud computing, wireless connectivity, and so on. And finally, again, going back into the loop where who is providing information to this digital twin in terms of data. So I have again collection of data using the sensors and feeding that information back to the digital twin world. So continuous loop, so interaction from the digital into the physical world and interaction from the physical back to the digital world. So it is a continuous cycle that follows, and that is where we look at what we defined as the digital transformation of the two entities, the physical entity and the digital entity. So moving on, some multiple applications of the digital twins technology where we are applying them. So manufacturing is one of the key ones, which is where since 2002 all the work has been started for the product life cycle management. Then comes the automobile sector, aerospace industry, healthcare. We are part of the London Digital Twin Research Center here at Middlesex University, and within our center, we have projects which are related to quite a few areas: manufacturing, automobile, healthcare, and communications. So we cover quite a few areas, and as part of infrastructure, we have structural health monitoring projects as well. So we look at structural health monitoring of bridges, of a couple of projects with Vietnam. So that was one of them. So giving you perspective on applications to use cases. Okay, so this is one of the first ones for manufacturing. What we have here is, as you can see on the left hand side, is the physical system, which is made up of two islands, and it has about 30 to 50 sensors. Okay, so multiple sensors. There are solenoids, there are capacitive sensors, there are infrared sensors, there is a camera unit which is based over there, RFID readers, conveyor belt, and all that. Now, if you consider all of those, you can model that into the virtual world replica wise, because you have, this is a Pesto cyber physical factory, the mini version of the uh, cyber physical factory, which would be deployed in the real world, and it is controlled via Siemens PLCs. Now, if you think about it, you are able to replicate this directly in Unity because the CAD files are available for each of these. So all we've done is imported them into Unity, but the key point is the two-way synchronization. So the two-way synchronization, which is here, how do we achieve that? Do we need some sort of connectivity between here and here? What sort of interface would you use? Would you use, Wi-Fi? You use wired? Would you use some other mechanisms? Direct connectivity, optical connections. So based upon that, you have the virtual world talking to the real world and vice versa. The idea here within the virtual world is to make sure that it is able to perform using the data it collects from the sensors from here and feeding it back to the virtual world. It is able to perform predictive maintenance, anomaly detection, optimize operations, scheduling, and the trajectory of the carrier. So on the conveyor belt, something is moving around. In real world, it should move around near real time. Okay, so that is where we are in terms of the implementation for manufacturing. Another use case, so critical infrastructure. So critical infrastructure, nuclear energy power plant. Okay, how do we define, how do we create a digital twin of a nuclear energy power plant? I need to have the exact information here, the size of all the four, the chimneys, the domes, the water cooling systems, the cooling towers. I need to know where the core is. I need to make sure that I have some sort of capabilities of computing and network systems. I have the physical phenomena of the actual operation of the the fusion process, and from there I can create the digital twin. But what am I using it for? So I'm using that for modeling and simulation, but at the same time I'm making sure that the safety of this physical asset is visible within the digital twin. I do not want it to break down. I do not want it to have any sort of issues. And I'm able to press a button within the digital twin. In case of an emergency, it can automatically turn the power plant off or reduce the temperatures, increase the cooling efficiency, etc. So, operations and management recommendations. or diagnostics and prognostics, and autonomous operations and control are what the digital twin provides for the lifespan of this nuclear power plant, um, which is what the scenario is in this case. Another one I mentioned is structural health monitoring. So oil rigs and gas rigs, where you are better off having some sort of a digital version of it in case of any problems happen that could be picked up based on historical data within the virtual world, and that can give recommendations to the physical world to perform certain tasks at a safe, you know at a safe tolerable level. Another example, which is the structural health monitoring, is the bridge. So this bridge collapsed over a period of time. The number of vehicles kept on increasing and increasing, and at one point, the without any monitoring in place, this bridge collapsed. We do not want the bridge to collapse, but instead you want to, throw in the sensors which are going to be looking at the structural health of this bridge and making sure it gives sufficient information to the user and to the people to make sure that the bridge is safe to travel. Okay, so another use case for um, structural health monitoring. So moving on, one of the key areas that I work in at the moment is this, which is automotive digital twins. So for autonomous cars, we are looking at uh, you know more on ADAS systems and how we can improve ADAS systems to have that autonomy for the vehicles to make decisions, and for having the normal user and the autonomous cars on the road at the same time without any problems. So, just to give you an example, unstructured traffic. So, India has a classic problem of unstructured traffic, meaning you are standing here at the traffic light. If you do not make a move, you have people going from all directions coming in front of you and going ahead, but you are going to be stuck. If that was the case for the autonomous car, the sensors are just going to keep on sensing and giving that information to the car to say you cannot move, there is a person passing by, or there is a bicycle passing by, or there is a bike passing by, or another car passing by, or a truck passing by, bus passing by, etc. So what does the autonomous car do in that case? So that is a very classic problem that we are trying to come to a possible solution, which is the case of automotive digital twins. Our cars are already smart enough in terms of, as long as there is connectivity, so 4G 5G connectivity in the car, the sensors are picking up all the information and sending it to the cloud, and in return you get as a feedback. So at times the physical system is also giving you feedback, but the virtual system is also providing that additional feedback for the safety aspect of the car and the lifespan, to increase the lifespan of the car. um, some other use cases are agriculture. So agriculture also belongs to the national interest in terms of critical infrastructure safety. Okay, purely because food is a necessity, and there all countries have the initiative for food security. Food security includes, for example, disease identification, weather service management. So if the weather is very dry and crops are going to fail, what could be the option here? What could be the alternatives? So the alternatives could be planned in the digital twin based upon weather service information, based upon current predictions, current sensor values, and so on. So here in this example, it's more about precision farming, increasing the crop yield, so yield prediction, and soil and climate modeling. So are we keeping the soil safe if we are using too many fertilizers, too many chemicals, etc.? Is the climate good enough for growing a particular crop? At what time is it good? So those aspects can be all predictive side of things, which can be part of your virtual world, which is the digital twin. If you look at Singapore, okay, Singapore has created this real life use case for the entire city. So a smart city has been developed using Dassault Systems software, which is the innovative city project. There are multiple links on YouTube available for you to look at how do you experience in 3D the actual city's virtual replica. So thinking about all those multiple use cases, you have federated digital twinning. So within federated digital twinning, you have the horizontal slices as well as you have the vertical slices. So if I'm looking at the horizontal aspects, okay, my my cyber physical systems, so my physical systems are mobility, agriculture, sky, construction, manufacturing, etc. I am passing all that information from sensors on this end to the cyberspace, okay, where cars have autonomous cars, for example, have multiple sensors for smart mobility services, power plants, or again for smart power plant systems, etc., which is where we define it to be as the service layer. So all of those systems can be part of these services. And then if I further bring it upwards to the upper digital twin layer, which is the Internet of Federated Digital Twins. Instead of Internet of Things, we are now calling it as Internet of Federated Digital Twins. All federated different types of twins are connected together to give you multiple other use case services. So your upper layer services in this case can be smart logistics, smart green city, car sharing services, etc. Okay, so first thing, the lower levels are already talking about monitoring of the sensors within the car for mobility purposes. But from there, I'm looking at upper service layer where I'm saying actually if a person is traveling from, let's say, Hyderabad to Bangalore and or maybe somewhere else, then if they are driving, which is probably quite a far distance and they're driving alone, but there are other users who may be able to share the trip, then car share service could be of use. But where are you going to be sitting in any car that you feel like? No, you will need some sort of recommendations. So the recommendations come from the lower level, which is the mobility service of the vehicles. Then comes from all these multiple use cases, what are the threats? There are, of course, going to be data threats. If I don't have end-to-end kind of encryption or some sort of, post-quantum cryptography being embedded, the scenario will be, yes, autonomous cars are lovely, but if one person can hack into one car or one network, they can control the entire fleet of autonomous cars. And if that happens, we've seen it all in number of movies that cars fly from parking lots or multiple cars are going in one direction, causing accident, causing traffic, and so on and so forth. So those are the threats that come along with the Internet of Digital Twins. And what are those type of threats? So the threats, you have data tampering, you have low quality data. So you can tamper the data in between while it's traveling from the physical asset to the cloud, to the digital twin. Low quality data, you can tamper the sensors, the physical sensors, and that means you are always going to get low quality data. Desynchronization of digital twins. If I have multiple federated twins, I can have out of sync of one. That means the entire network of digital twins is out of sync. Model inconsistency. The modeling that happens within the twins, the prediction, the other aspects, that can be a inconsistency there. poisoning data or content. So I could be somebody as a joining the network which I'm not supposed to, and the typical, I'm injecting false data and I'm creating false content. So data and content poisoning. Having said all those, the 1 to 5, the next section, which is 6 to 10, okay, is more about semantic type of information. So as a digital twin approach, I am not going to be able, doesn't matter whether I have 5G or 6G type of communication, the best and the best of the operators, etc. And my car has got dedicated network, or my manufacturing unit has got dedicated network for transferring data to the digital twin. But I'm not going to be sending every smallest amount of sensing data. I need to make sure that I send just the useful information or event triggered information, so that I'm not congesting the network, which is where we define it to be as semantic information. So semantic data knowledge poisoning, semantic adversarials, model poisoning, backup data, etc. They all are part of this overall area of threats that exists for digital twins. So when we are thinking of creating digital twins, we need to make sure that we embed security strictly within the creation of the digital twins. What sort of mechanism you use, whether you use blockchain, whether you use some encryptions mechanisms, you use post quantum cryptography, etc. It all boils down to the application. Is my application giving me value for money? Is my digital twin giving me substantial outputs in terms of operational efficiency, in terms of intrusion detection uh, systems and so on, predictions? Then yes, I'm going to be applying all those. So as an example, for the internet of digital twins, what sort of semantic related attacks are possible? The key one here, just a simple eavesdropping attack. I have an original image which, via the semantic channel encoder, I am passing very little information via the wireless environment, and I am decoding what I have received while I reconstruct the data. So pretty much close enough to the original image. But if I have an eavesdropper at that point, the eavesdropper is also able to replicate something, but nowhere close to what the original image was. The other example, traveling near a lake, and you can see that there is no further, there is a lake and the road ends here. But if I have an adversarial attack at the transmitter side, or in between prior to receiving, then the problem that I will face, in the first case, test data which is clear, I will be making sure that what prediction I'm making is ahead is a lake and there is no traffic that is allowed. So if this was an autonomous car, it would go and stop there because it receives that information correctly. However, I have some sort of, at the transmitter end, or at the second case where I have, some sort of adversarial injection of, or somebody is trying to get in to the network, then they will reconstruct this information, and the digital twin is going to say, hang on, what I've generated is this, which is, the road is clear, pass with confidence. The autonomous car is going to be able to pass with confidence, but the reality at that point is going to be, it's going to fall into the lake. Likewise, poisoning attacks. So right from the raw data point where poisoning happens via an adversary, all the way to the end, everything gets poisoned. So whether it is the encoding, the decoding part, what it receives is the incorrect result, which is basically the poisoned information. So these are the type of attacks which we need to be very much careful of. when it comes to making sure that the design incorporates cybersecurity within digital twins. So, what are the steps for creating the digital twin? So, this is where the architecture and the technologies and other things come into play. Uh, there is no right or wrong way, but Bosch have published this information, which is what are the steps for creating the digital twin the right way. Uh, Access to historical data and acquiring real-time data through sensors. So that's step number one. Data integration and fidelity and allegiance. How do I know that the data that I collect is 100% true? And based on the models that I choose, my fidelity of the digital twin is close to 100%. Okay. So gather data, process, apply the knowledge, simulate, visualize, and causality. So at that point, I am able to predict all these. From the digital model, I'm able to predict what the failure models are going to be looking like for my operating physical asset by running simulations within the digital twin core, reaching to visualization of the failure models and reaching to the point where I can predict that this physical asset is going to be failing at a particular point. Okay. Um, so number of aspects, so collecting the right data, attributes of telemetry, so on. So collecting the right data is quite critical, okay? Especially the areas where you have sensor failures, you have telemetry inconsistencies. So you may be sending the data, but there might be a huge delay. Let's say even 5 seconds or 10 seconds or 1 second delay is critical when it comes to predicting what the next option should be for a manufacturing unit or for an autonomous car or for a nuclear power station. If there is a spike in the temperature readings in the nuclear power station, but they are transmitted with a delay, so the inconsistency happens because of the delay within the network, then we also have a problem. So those are the aspects that needs to be considered in this scenario. So what's the reality here between a simulation versus a digital twin? Okay. If I look at simulation, it is typically disconnected from the real world data, whereas digital twins, they have real-time connection to the physical entity or assets, and they receive the sensor data. They keep the sensor data on the side as well. They also have access to the historical data, and then they are able to simulate next what if scenarios. Okay. And based upon the what if scenarios, it is able to provide bidirectional data flow to make sure that you are able to actuate the process. Uh, Based on predetermined scenario simulations, if I'm running a, let's say, intelligent transportation system scenario, I'm going to have a predetermined scenario where I'm going to say, I'm traveling from road A to B. I have X number of intersections. I have X number of single lane roads, and so on and so forth. And that's a predetermined scenario. But on the other side, the digital twin should be able to predict based upon the map data, based upon the sensor data, based upon the GPS information, saying you are traveling in this direction, your map, your route is this, and you should be traveling at so and so speed. The road is clear ahead, and all sorts of other information. Life cycle focus, past, present, and future. So historical data, current sensor future, simulated information. But that simulated information is based upon the past and the present, not just predetermined scenarios. Okay. So there is a huge difference between digital twinning versus simulation. Simulation now can be part of what we define as co-simulation, as part of something which is embedded within digital twins to replicate and to come up with predictive scenarios as opposed to predetermined scenarios. Maturity levels. So, maturity levels based upon technology versus what is the requirement of the business. Okay, so performance using the technology push, and transformation using the business pull. Okay, what is the business requirement? I have multiple maturity levels, from a simple description or descriptive to what is happening. So I can just say, take the sensor data, create a digital shadow, and I can say what is descriptive, what is happening. To diagnostic, why is it happening? I'm able, using my AI models, using my modeling within the digital twin inside my framework, I'm able to say, why is this happening? What caused it? Let me fetch historical data. Let me fetch real-time sensor inputs and see what's gone wrong. From there, I go to the predictive level where I say, what will happen if the sensor is values are these, but they go to certain other values. So I'm able to predict that the conveyor belt is going to it's going to start wearing off very badly in the next 10 days. To From prediction to prescriptive, the autonomous system should be able to, basically, within the digital twin there should be a what if scenario, and from what if scenario, what is the outcome of it. So that is prescriptive, which says we need to call that maintenance engineer in the next 9 days, before on the 10th day your system is going to fail. So that is called prescriptive. And from there to completely autonomous. So those are the levels of digital twin. Currently, most of the systems, most of what has been published all across the globe in terms of digital twins are here: descriptive and diagnostic. There are some works which are part of prediction, but majority of the work is here, which is descriptive and diagnostics. Multiple tools available for visualization of creating those digital twins. So what softwares do we have? What specialist uh, software that we can get hold of? From industrial platforms, we have the Siemens advanced 3D visualization, so that is for manufacturing units. GE's industrial digital twin framework, again, which is for real-time dashboard visualization and analytics. So if I go back quickly to that maturity level, you can clearly see diagnostic and descriptive. Siemens and Genix, they both are diagnostic and descriptive. So this is still at the same maturity level, which I was telling you, but in industry environment as well. Another one key is Omniverse. So for large scale virtual worlds, sharing of AI generated 3D content. So you are additionally creating data streams of AI generated information, which is offered by NVIDIA. And after that, you have these open source, which are very useful. For researchers like us, getting access to these can be very tricky uh, because of the cost issues, because of licensing, etc., and because of also geographical locations as well. So instead, there are these, which is the Unity, Cesium, and Eclipse Ditto. So those are my open source favorites, especially Unity. Our work at Middlesex, most of it happens on Unity for visualization. Uh, so we create our digital twins within the Unity. We have our network, per se, communications network, where we talk to the physical world. So here's an example of your critical infrastructure type, digital twins. This is from GE. I'm gonna go quickly. That's one of the examples, and the other example we have is our own. Like I said, that the Middlesex University's um, uh, CPS digital twin. So we have plenty of. If you subscribe here, for example, to London Digital Twin Research Center, you have plenty of useful information and videos that are available there. And also the workshops and the events that we do at the London Digital Twin Research Center, they are all recorded, and there are lots of playlists available. So this is our version, just to give you a quick brief overview. So you can see there is a slight delay. So it is near real time. It is not 100% real time. Um, let's see some more. Uh, and yeah, so this was done basically using you know TCP/IP socket programming for the PLC's connectivity and sensor management via Raspberry Pi. So very basic tools, very simplistic tools for prototyping. Of course, when you want to go from prototyping to a particular TRL readiness, things change, which is something that also needs to be looked into. So, lastly, what are the existing challenges that exist within the research community for digital twins? Interoperability. Everybody wants to have their own version of the pie of digital twins, but where is the interoperability? If I want interoperability, I need to create multiple other interfaces, which is where the challenge lies. I've already discussed security and privacy as one of the key concerns. Scalability, up to an extent, the more the amount of data that you collect for your digital twin to learn, there are going to be problems in terms of scalability, because where will you keep on storing that historical data for the digital twin to utilize? Skills gap is one of the key ones, which probably, I hope that this workshop is going to reduce that, especially on AI driven safety critical infrastructure aspects, and of course cultural and organizational change. So if you look, we saw those examples of GE, the power grid, and other areas. Where would that change be hitting the most? It would be at that organizational level. So those aspects need to be looked into. So just before I pause, I have this thing to share. Interconnected digital twins. I have my social digital twins. I have my economy. I have my environment, and I have multiple in between: the connected grid, the building, the city, the vehicles, the factories, all of it connected into one, you know, twin of a twin. So that is where the interconnectivity happens. But what are the key enabling technologies? And I will go back to my 5G and 6G, because without a well-established connectivity framework, these are worthless. They can be independent, but they cannot be connected into that entire, single digital twin, looking out for the social, economical, and environmental aspects of the the community. Right. So some references here, and thank you. And yeah, I am open for questions if you have any.
Hello. What is the difference between metaverse and digital twins? Because here L&T says that they are using metaverse for constructions in India.
Yes. So metaverse is the concept name for twins of twins. So multiple digital twins, when they are federated together, and you have federated digital twins combined together, you are trying to come up to that framework of metaverse.
Okay, thank you.
But to per se, I would say that to say that you are using metaverse for a particular scenario or a use case, that is a bit of an overkill from my perspective. I would rather call
No,
it to be a digital twin,
they are using
because
it.
metaverse.
They are using it. We are seeing from house they will operate, and any construction related things they tell it through that only.
Yeah. So when they say that it is metaverse, so when you bring in AR VR technologies, for
Yeah.
example,
Yeah.
if you are using AR VR, you can scan through. For example, if you have a video of your construction site, including all the equipment which are embedded within, now you bring that video into the AR VR headset, and once you have that, you are able to control those individual, how to say,
Activities.
uh, the activities that happen at the construction site as part of actuation process
Yes.
of the digital twin or the metaverse.
Thank you, sir.
So now it looks like there is no other question. So I would like to thank Dr. Purab sir. Yeah.
Thank you.
Sir, there is a one question.
Yeah.
So he is asking that migrational data flow is there, how it is getting added to the digital twin?
Migrational data flow being added to the digital twin.
Yeah.
In which particular sector are we talking about in terms of
Sir, you told one of the feature is bidirectional data flow in between the
Yeah.
simulator and the digital twin. So what is the
Yeah.
advantage of this bidirectional data flow?
No, what I meant by bidirectional data flow is you are able to control the physical asset from the digital twin. So if I push a button, or if I push a particular, if I give an action within the digital twin, that will be visible within the physical world. So as an example, that construction sector that one of them asked the question, if I'm able to control from the virtual world a particular, let's say, a caterpillar or a JCB machine digging equipment, then that means the digging equipment is able to predict, and via the sensors it is able to send information to the digital world to say how much it has reached in terms of the depth. Okay, but on the digital side, the digital twin is able to run some simulations and say your thermal properties are fine, your speed is slow, so can you increase the speed, and it gives that information back to the as an actuation in the physical world. So that is what we mean by bidirectional data flow.
Okay, okay.
So from online audience, is there any question? No, I think there is no question. So I would like to thank Dr. Purab sir taking out time out of his busy schedule and giving us information about a topic which is going to be the future and is going to change the core industry like anything. And I know this will bring a great revolution in the core industry. So thank you, Dr. Purab, for your
Thank
time
you.
and expertise sharing with us.
Thank you very much. I hope you all enjoyed the session. Right. Thank you.
Okay. Bye bye. See you.
Bye. Bye.